part 2 of this function generator and look at the quality of the signal through the fast Fourier transform analysis. Again, the maximum generated internally by calculation on the internal function is 25 megahertz, and with that you have a nice clean shape. However, you cannot go further than that, so it limits yourself to 25. One trick I use to get further, this is a 10 megahertz 1x times 1, so one shape. So we go back to 10 from 25 because the entire 8K pixel or 8K point table is cycled to 10 megahertz. So if you draw a sine wave, a single phase of a sine wave, you end up with 10 megahertz. So it was loaded 10 megahertz. This is the shape. Just to show you frequency, right? 10 megahertz for a table that is generated with times one cycle of sine wave. You got 1 for 1, but you could pick a more aggressive one. This is 10 megahertz times 5, which is the best shape that I've found without too much of a distortion, and we will look at it through the FFT analysis. So the shape is stable, it's nice. We start to see some dancing a little bit, but very small. One way to look at it is through the math function FFT. Let's put it there. Let's declutter some stuff. Frequency, we know that. Remove. By default, the FFT gives you the auto setting. What it does is simply center the most visible frequency that it sees, but there is not much information. And by the way, that's a little bit of what I want to show you. For FFT to learn, there is a lot of math, but there is a more simpler way to explain this. If you were to draw a paper, on a paper, the sine wave, you will probably put some point over this shape, and you will try to define what is the sine wave. So the more point you add, the more defined is the sine wave. That's the same thing for this scope. It has to sample at some point. Right now it's sampled very fast, 125 gigasample per second, but it's only 125 points, so not that much. So if you were to having a lower frequency than that, let's say, just to show you what I mean, this is the minimum 25 point on the entire display. So the lowest frequency you have is this, but you can have a possibility of the scope to have a lot of sample, but there is only 25, so you don't have enough point to understand what is composing. So if you want to look at the noise outside of the main frequency, you need to be able to sample outside. So one way to do that is to extend the number of points where you can sample. So I have I don't know, about 20 something. So now we could see on each side of the frequency, and again this is controlled by this. So the one way to look at it is center and span. So it's around 50 megahertz, and it spans 100 from one end to the other, from 0 to 100. So we are center. You could have the same control from 0 to 100, or center at 50 with 100 span. So it's the same thing. Um, there is some function that you could play with. This is related to the math, but the only thing to pick out is it's convolve the result that you got here with a shape, and it changed the result. Depending on the math analysis that you want to do, you pick the one that makes sense. They are all of them very wide. The only useful one is amming and anning, and their objective is to find the center frequency. Try to define the peak as small as possible. So amming is probably the best one because it gives the least width for the peak. So if you want to identify a peak, use amming. But if you want to look at the signal to noise, you're better with Blackman because the signal to noise get lower. You don't have much definition on the position of the peak, but you got everything related to analysis if there is a peak. I see here at 0 frequency there is something. So let's work with that one because we want to know what's happening with frequency. The other thing we need to let's put start end. Right now we are at 125. By the way, once you got this display in here, you could zoom on it, but it's not very useful. Just work only with the this frequency distribution from 0 to 100. The peak maximum frequency that the scope could give you is half of this, because there is the sampling theory. You need to have 2 points per sine wave cycle, so the maximum understand calculation frequency is half of that. So let's try that. So maximum is 625 megahertz. You won't be able to achieve anything else. Now we got something interesting. So we got our 50 megahertz here, and we got the distribution of all other frequency and the signal to noise. This is the thing we want to look at. We can change the sampling. Right now it's 200 nanosecond. If I decrease the number of pixel, it's still 121 gigasample per second, but now I have less points, so the information is not good. So if you want to evaluate the signal to noise, you want to increase this. So 15 nanosecond per division, 100, and the more point I had, the more definition I have on the scope, and the more 6K, 12K point, 1 microsecond, and the more I had, the more signal to noise I get. The noise floor go lower. So we could go up to a certain point, and that's probably the maximum. The more point I have, of course, the slower the scope gets. And now something happened. The amount of memory is limited on the scope, so for its analysis. So at 125 gigasample per second, it is able to put 625 point on the display. And could have a look at the display again just to show you. So it's over here, but if we're to activate the zoom, we could zoom on it. So it's still the sine wave, but basically what you have is from the entire 50 microsecond, if you zoom on it, you got your sine wave, and you see it start to dance now. So let's get rid of this. So I was showing 125 maximum sampling rate of the scope, but if I increase the I have to select this. I have to turn off the zoom, so the button will now work again. So 250, 625 kilo point, and if I try to add the more point, it does not add more point, it's reduced the sampling rate. So it's 625 instead of 125 gigasample, but there is not enough memory to put 100 microsecond per division to record the sine wave on the time display. But on the FFT display, you see the consequence. So it has to reduce the sampling rate to record over that time. And the more you increase the time, the less sampling rate it gets. So you are limited here to this value. And by the way, that's the same thing if I put back 125 gigasample, but I activate the display number 2, the canal number 2. So again, the sampling rate reduced because now it needs to display 2 trays instead of just 1. So we could deactivate this one. Display number 2, turn that thing off, and then we got what we got here. You could play with the memory manually. Memory depth, let's put that to maximum. You don't see any change. 25, no change. 10 meg point, 1 meg point, no change. So the internal calculation is probably in between this. So 100k point, not enough point. 1 meg point, we got something almost full for the analysis. So if you put that to auto, it's happy with a 0.6 meg point. So it's deciding what is best. Okay, from this setup, we have the maximum sample. We could sample up to 625. You could play with the display simply by dragging it. You cannot go beyond the frequency. You could move it left and right, but what will happen is it will zoom on the display. So right now I'm from something 0 to 100. If you pick something interesting, you go back and put even number here. For the scale, 22 point something, let's put something more easy. 20 dB per division vertical. And the offset, this looks a lot like 90 dB offset. So with this adjustment, now the scale is evenly placed, and the same thing for the scale. And now we could look at what is the height of the central peak, 50 megahertz, with respect to the noise all over. So I will put back maximum 625 meg from 0, and let's look at the noise. So the worst noise is at this point. So the sine wave is 50 megahertz plus a contribution unwanted at 312 megahertz, another here at 570, something like that. And it's repeat itself many times, so 1 time, 2 times, 3 times, things like that. So basically, if you look at the worst offender, you will have an indication of what is the noise. One way to do it is you activate the peak search. From peak search, you define here the number of peak that you search for. So it will give you the from amplitude point, which are the highest, and you now need to trigger on something. The scope doesn't know where to look. Of course, it's fine the first one at 50 megahertz, but let's increase the sensitivity, or just increase by controlling the button. So no peak up to 44, negative. Oh, at 49 I got 1 peak, and this one is almost 0 frequency. So it's the DC component. It's sometimes the leftmost part of the display. This is not part of the signal to noise, it's part of the DC component. So if I could adjust the level to have a 0 dB component, this will disappear. One way to make this thing disappear, 122, if I clip the analyzers to, let's say, 2 kilohertz, 2 kilohertz, and now that peak just disappear. And we could further continue our analysis. For the peak search is activated through here. Let's continue. So now we're looking for every noise component up to minus 49 dB. And let's put the cursor here. And if I reduce 50, 52, 56, minus 60, so we have to go very low, and some component appear at 65 dB. And let's stop this search at this point. So the first component, of course, is the main one, minus 60 dB volt. You could adjust the amplitude of the sine wave to make it 0 dB. So it's a rather small signal, but the important is the ratio between the first and the second component. This is the signal, the remaining is the noise. 66 dB, and this minus this give you about 50 dB of signal to noise ratio for this frequency generated by the generator. We could look differently with this. You have cursor. You could put the cursor on the top component, and you could search graphically. Well, let's do something. I don't want to have the display. Let's change to none. Label is off already, but now it's easier to look at. So let's go back to the cursor. You could drag it here. So it's about there. It's easier to drag it. Strangely, they put the display on top. If there were on the left part instead of the right part, we could be able to drag it and looking at the result. So we got 52 dB delta of signal to noise from this thing. And now we could make it work again, and we'll see what's happened if I increase the frequency. But instead of using the one that I've put on the website, I will use a special one. This time on my USB key. This is times 6, 10 megahertz times 6. Select this file. Okay, load. And with this, I will be able to show you the signal to noise is not that good. So it's 1 kilohertz. That's not the right one. Let's have a look again. I think I have a better one on internal memory. Times 6. Load. Operation fail. Oh, so where's the big one? I could use the time 10. 10 megahertz time 10. Do you have this thing here? 10 megahertz time 1, 10 megahertz times 5. This is a nice 50. 10 megahertz times 6. It was supposed to be that one, but it failed to load. Let's try again. Load. Success. Okay, must have done something bad. Oh, I select the name of the file and not highlight the right part. So if we look again, this is now 10 megahertz times 6. So the frequency now is, if we add again the measure frequency, so it's C something like 64. Let's play with the frequency a little bit. So 10 times 6, 60. If I reduce a little bit the frequency, we'll see the noise component move. So very quickly, from, let's go back to 50 megahertz. Signal to noise is where the cursor are. So 52 dB of signal to noise. If I go to 54, 55, you see all the peak of noise going up. The most offender is here and here. So let's move the analysis up to 124. Use this, change. I don't want to look at everything. I just want to look at 124 megahertz. So we span a little bit. Here's the fancy noise, and if we move the cursor, amplitude has gone down a little bit. We are only at 40 dB for 50-ish. So it has difficulty to measure the frequency now because it's noisy. And if I go even higher frequency, let's move that thing over here. So 9.7 on the table. If I increase that, you will see the peak going up and up, and at 60 it's probably the last time we got something almost useful. And let's look at it. Now we are at something like that, 31 dB only. So it's 30 dB at 60 megahertz, but it's not very beautiful. Let's look at the wave. Let's put everything there. Waveform view, add to display. Let's get rid of this and activate the zoom. So I could look at the zoom this way. So the entire memory, 50 micros. Well, you could reduce the number of samples. It won't change the frequency that is displayed, but if you zoom on it, you will end up at the same place. And you see, well, it's there. It's 60 megahertz, but it's dancing a lot, and it's not very. If you were to do some noise analysis or filtering as a source, it's not a clean source, so you need to do something. Let's reduce again the frequency and show on the right the where we are. 10 megahertz for the sampling table. Reduce that to something like 54. It's still dancing. At 50, it's about there. It's still dancing, but it begins to be more clean. And of course, you go lower, then it gets at some point kind of stable, and you get probably more stable frequency by not using the table, but the internal frequency generator by calculation is 25. So let's play with that. Instead of arbitrary, go to sine, go to 25 meg, amplitude about the same. Well, it's dancing as, would say, the same. So that's way with the FFT. I will try to do the same with the old DS1054 just for the fun of it.